Right, so we're looking at Newton's third law now. So we've looked at first, which is the law of inertia. This is probably the most famous of the laws, the one that if you walk up the side of the street, it's the one they're most likely to know. It's the law of equals and opposites. So every action has an equal and opposite reaction. And when they say action, what they talk about is force. Every time you apply a force to something, it applies a force back on you. That's essentially what the law is all about. Okay, but what does that really mean when we talk about in our life? What is that sort of talking about? So rather than tell you, I thought I'd ask a question. The question is, have you ever tried walking on ice? Or something slippery for that matter, it doesn't matter what it is, but ice is a really good example. Okay, so if you've ever been somewhere really cold and you're trying to walk on ice, you'll know that it's a little bit challenging. So I want you to think about what happened and then try and explain why. So I'll give you a couple of seconds to think about what's occurred. So when you're walking on ice, what occurs if you're at the ice skating rink, you haven't got skates on, and why does that occur? Before I give away the answer, I'll sort of give you a bit about how we walk. I'll tell you about how we walk. So walking is obviously a pretty important skill. When we walk, what's going on is that we are applying a force on the earth. So when we walk, we are using friction between our foot and the earth to push ourselves, pushes a force, to push ourselves forward. Okay? You may not realise this, but you're also applying a force on the earth. Okay? So when you walk, you push off the earth is also pushing off on you. The size of that force is exactly the same as the force that you're applying on the earth, but in the opposite direction. So that's where it's applying an equal and opposite force on you. So you're pushing on the earth is pushing on you. That's how we walk. If we took away friction, what would happen is we wouldn't be able to apply a force on the earth, and therefore the earth wouldn't be able to apply a force on us. So when we're walking on ice, what's occurring is the lack of friction is not enabling us to push off the earth, which causes, so we don't apply a force on the earth, which means that we fall forward because there's no force being applied. And the reason that occurs is because it's not applying a force back on us. Okay? So without friction, we can't walk. It's really, really important, friction. We push on the earth, and the earth pushes back on us. So on this question, why doesn't the earth move? Because if we're applying a force to the earth, Newton's second law says F equals ma. Surely, if we're applying a force to the earth, shouldn't the earth receive some acceleration? The answer is it does. The earth does receive an acceleration from us. However, our mass relative to the mass of the earth is pathetically small. We are such a small thing relative to the earth. So because of the size of the earth, yes, we do apply a force on it, but the magnitude of the acceleration is so teeny tiny we don't even notice it. Also, you've got to consider the fact that there are forces being applied in every part of the earth, which enables that to cancel and add up. Okay, so if you've got two people standing on opposite sides of the earth and they both jump, obviously their forces are going to cancel out. If you've got two people on the same side of the earth jumping and there's nothing on the other side, then their forces will add together. However, the size of their force relative to the mass of the earth is going to create very little acceleration. Cool? So just some other examples, and I'll just try and get rid of that because the glare is pretty ordinary. So I'll just move that over here. So some other examples of where we might see that where we might see Newton's third law applying. And we're going to see some pretty ordinary diagrams here, but I thought I'd show them out. So when we're kicking a ball, so this is a pretty common example. If I've got a ball here, and here's my ordinary looking foot, okay, if it applies a force on the ball that way, the ball will apply an equal force, and I'll use the red. So that's the action force is the one in the blue. The red is the reaction force. Now you'll notice the magnitude of the force is the same, the direction is the opposite. Okay, so if we're shooting a gun, so again we're about to see my great drawing skills fired here. So here's Bob with his hand. I don't know why Bob's got that sort of thing going on. When Bob shoots the bullet out of the gun, okay, the action force is in blue. That's the action force. The reaction force is what forces the gun or makes Bob have to strain his muscles to prevent the gun from firing back. Even sitting on your chair. So if you think about right now when you're sitting at home, enjoying your isolation, you've got your little chair, and again, there's a reason I'm teaching physics, not art. You've got your chair. You're applying a force on the chair. That's the wrong colour. You're applying a force on the chair downwards. You're applying a force on the chair downwards. Okay, and the chair is applying a force on you equal and opposite upwards. How do you know that force is there? Well, if you took the chair away, what would happen, firstly? And secondly, you know that you're not accelerating. So you know those forces are equal because when you're sitting on your chair, there is no acceleration. If there's no acceleration, F equals ma, there must be no force. So if there's no force, it means that they're cancelling out. So you've got the same amount applying down as you do upwards. Therefore, there is an equal and opposite force, proving Newton's third law. Just some examples of where you'll see it. We're going to move into free body diagrams later on, which are just where I replace these with little boxes, and we show the same thing with free body diagrams. But that's an example of where we might see Newton's third law applying. On Earth, essentially it's all about equal and opposite forces. Anytime you apply a force to anything, whether it's the ground, a ball, an object, pushing something across the table, it's applying the same force back on you. Okay? Very, very good.